Hello to everybody and welcome back to those who were with us the lecture before. We start now with a very, very interesting lecture about the life in the universe. Where is everybody searching for life in the universe, which is going to be given by Professor Amedeo Balbi, who is professor at the University of Rome Tor Vergata, but not only professor there, he's doing a lot of activity of dissemination and education activity on YouTube channel. And he's also, I am very pleased that we are colleagues in this Foundational Question Institute American Association, where we do some research about fundamental physics. So I leave the floor to Amedeo to tell us something about the search for life in the universe. And I thank him for being here with us to this INSPYRE 2020 edition. Please, Amedeo.
Hello, good morning. Thank you, Catalina, for the invitation, for being able to speak to you guys, although remotely, because we are now, forced to not to move too much around, and we have to be careful about that. And the title of my talk, which is "Where is Everybody?" Searching for life in the universe. Where is everybody does not refer to the lockdown, does not refer to the fact that if you look at our streets these days, you cannot find anyone around. But this is a different question, is the fact that we cannot find anyone around in the universe. Actually, we haven't been able until now to find any proof that there is life elsewhere in the universe beyond Earth. But still, this is something that we ask ourselves. We ask ourselves if there is any life in the universe. And so why is that we couldn't find any evidence yet? And I will try to explain why. And of course, let me remind you where this question, where is everybody, comes from, because there is a funny anecdote around this question. The story is that the question was first asked in this formulation, at least, by physicist Enrico Fermi in the 50s, in 1950s. Enrico Fermi was working in the US, and apparently one day he was having a discussion with some colleagues, with some other physicists, about this comic, this cartoon that appeared on the New Yorker at the time. You see that there is a timestamp there. It's 1950, I guess. And this comic, this cartoon, was showing some aliens that reached the Earth by some starship, and that they were getting rid. They were taking some trash cans. And the reason for this comic for this cartoon was that at that time, many people around the US were citing UFOs. Okay, there was this hysteria about people seeing lights in the sky and thinking that they were alien spaceships. And also at the same time in New York, trash cans were disappearing because someone was stealing those trash cans. And so the comic was referring to these facts and was putting together the two facts together with one single explanation. And so Fermi was joking that it was a good explanation, actually, because there was one explanation for two different facts. Of course, they were just joking. No one was actually believing that UFOs were actually spaceship. But the point was that Fermi started doing some mental calculation about the probability that the galaxy was inhabited, that there were other planets in the galaxy where there was life. And he immediately realized that the probability for that apparently was very large, because there are many, many, many stars in the galaxy. Our galaxy contains hundreds of billions of stars, so it's a huge number. And actually, I mean, there is no reason not to think that any of those stars also have planets. Okay, so there are hundreds of billions of planets in the galaxy. And the other interesting fact is that the stars existing in the galaxy are much older on average than our star. So our star, the sun, has only 5 billion years, but there are stars in the galaxy that have 6, 7, 8, 9, 10 billion years, so that are much older than ours. And so Fermi was thinking, well, if there are all those stars, and all those stars are much older than the sun, there should be many other planets where life had many billion years of time to develop. And so the galaxy should be full of life. So how come we don't see any evidence? Where is everybody? That is the question. Okay, so the question is still unanswered. We don't have an answer to that, but we are trying to get a scientific answer to this question, and we don't have that many facts at the moment. So we are trying to get some new information, okay? And let me tell you what are the main facts that we have. One fact is that we know the history of the universe. The history of the universe, it's something that we learned in the past 50 years, more or less. We know that the universe began in a very hot, dense state that we call the Big Bang, and this happened roughly 14 billion years ago. And then time passed, and as time passed, things happened. And one of the things that happened is that stars formed, and galaxies and planets on these stars. So it took some time, but eventually we ended up with a universe full of stars. And so the situation evolved and changed a lot. And in fact, I mean, most of this picture now is very clear. We know very well what happened in the universe in the past 14 billion years. We know all the forces playing around. We know all the physical mechanisms, and we can tell how we went from the beginning to now, okay? All this overall picture is very clear. But then in this picture, which is very clear, there is another picture, another story, which is a different story. It's not the story of the universe, it's the story of life on Earth. And also this story now is very clear. We have fossil evidence, we have records of the geological history of the Earth. We know that the Earth formed around 4.5 billion years ago. So the story of Earth is much shorter than the story of the universe. And during this story, for 4.5 billion years, also many things happened on Earth. And one of the things that happened on Earth, which is very important for us, is that life appeared. Okay, we wouldn't be here today having this discussion if life didn't appear on Earth. And the interesting thing, one of the things that we know is that life appeared very early in the history of the universe, of the Earth, because the Earth is 4.5 billion years old, and life is probably 3.5 billion years old. Someone says also, based on some evidence, that life may have appeared on Earth as early as 4 billion years ago. Okay, which means that life basically was on Earth for almost the entire history of the planet. And not only that, but the history of life was tightly related to the history of the Earth as a planet, so that the planet changed because there was life on it, and life changed because the planet changed. So it was a very tight relation, okay? One of the things, for example, which is very important for what we will tell in the remaining of this lecture, is that at some point around 2.5 billion years ago, there was a huge increase of oxygen in the atmosphere. And we now know that this increase of oxygen in the atmosphere was in some way also related to the fact that life was on Earth, because photosynthetic life, plants, and bacteria that use the light of the sun and photosynthesis, they release oxygen, free oxygen in the atmosphere. So one of the sources of oxygen in the atmosphere is life. And so it's a complicated story, okay? But basically this is all we know. And it's very interesting because it tells us something about what life is. But the problem is, and this is a huge problem that goes back to the question that Fermi was asking, where is everybody? The problem is that we only have one planet that we know for certain that has life on it. And so everything we say about life is related to this single case. We only know one example of life. And unfortunately, it's very difficult to do science when you only have one data. So what we're trying to do in these years, in particular in astrobiology, which is a discipline which puts together astrophysics and biology, we're trying to put together these two stories, the story of the universe and the story of life. We're trying to have a single picture of all that happened, okay? But, as I said, this is very complicated because we only have one example. And unfortunately, one thing that I want to be clear, that I want to say, I want to be clear on that, is that everything we can conclude by one single data is not enough. We cannot say anything general, okay? But let me try to be a bit more practical on that, and let's try to see not how life originated, which is very complicated to explain. Charles Darwin famously said that it was hard to say what happened at the origin of life, but then he speculated that life probably appeared when the right conditions were present on our planet. And then other people in the 20th century, for example, Oparin, who was a Russian scientist, evolved and developed this picture and imagined that life appeared on Earth because there were some chemical reactions, okay, that created the first molecules and the first replication and the first cells and so on, okay? But unfortunately, the picture is very unclear. We don't know exactly what happened. It's very hard to reconstruct what happened at the origin of life. So what we're trying to do is something more humble, more modest. We're not trying to say exactly how life appeared. As astrobiologists, what we're trying to say is, well, let's look for the right conditions for life, not for the mechanism, because we don't know exactly what the mechanism is. Let's just look for the places in the universe where there can be the right conditions. And then let's go look and let's see if there is any life there, okay? And the problem is that, well, saying what life is complicated. We don't have a single definition, but we have a clear idea of what the conditions for life is. One condition is that there must be some chemistry involved and some complicated chemistry of carbon, okay? Because carbon is a molecule that is an atom that allows to form complex molecules. And these complex molecules can do interesting stuff. But if you don't have carbon involved, it's very difficult to have this chemistry going on. So the first basic ingredient of life is complex molecules based on carbon. Carbon, oxygen, and hydrogen are the most important constituents of life on Earth. So this is the first ingredient. Second ingredient is that you have to have some energy, some free energy to do work and to do all the things that living systems do. And fortunately, we have stars in the universe, and so we have an abundant and frequent source of energy in the universe. And then the third ingredient is much more difficult to find because we believe that one of the basic ingredients of life is liquid water. So when we're looking for life in the universe and for places where life can be, we're looking for these three conditions: carbon, complex organic molecules, energy, And the first two ingredients are pretty easy to find in the universe. We find organic molecules also in meteorites, in interstellar space, mostly. It's relatively easy to find these molecules. And then energy is also easy to find. But what is more difficult to find is to find water in liquid state, because water in itself is an abundant molecule in the universe, but water in liquid state is not so easy to find. And then, of course, we don't know what happens. We don't know exactly what happens, but we know that we have to allow for some time, because you want to have this condition for a long enough time on a planetary surface in order to hope that something like life, as complex as life, can appear. Okay, so where can we find these conditions? Well, we have a starting point. The starting point is to look for places in what the astronomers call the habitable zone. Habitable zone doesn't mean that we're sure that there is life there, but it's only a place where we believe that there may be the conditions for life. And this habitable zone is simply defined as the distance from the star where the temperature is compatible with the presence of liquid water. So the planet has not to be too close to the star, because otherwise it's too hot, and it has not to be too far from the star, because otherwise it's too cold. It has to be in the interval of location, which is just right for water to be in the liquid state. Of course, this is much more complicated than that. Okay, I don't want to give the impression that it's too easy, because it's not. And to give you an example that is not easy, let's look at our system, and let's pretend that we are astronomers looking at our system from far enough from their planet. So we are looking at this system, and we discover that there are 4 rocky planets, and these 4 rocky planets around the stars, 3 out of these 4 rocky planets are in the habitable zone. So if I do a calculation of the orbit, I find that they are compatible with the presence of liquid water. But unfortunately, we know that there are only 1 planet of these 3 planets is in fact habitable, and in fact has liquid water on that. And why is that? It's because it's more complicated than that. So we have these 3 planets, Venus, the Earth, and Mars. They are all in the range of distance where there could be liquid water, but only Earth has liquid water on that. And why is that? It's because, as we will try to see in the remaining of this talk, the story is more complicated. So if you have questions now on this first part of the talk, you can ask questions, and then we can go to the second part.
Yes, so Amedeo, there is one question asked by Mattia, who is asking if silicon is a possible substitute for carbon.
This is a question that is often asked, and there is some science fiction about that we have silicon, because silicon has some superficial resemblance with carbon, because they have the same number of electrons that can, in principle, have bonds to other atoms. But the reality is that if you look at the chemistry of silicon, is much less interesting than the chemistry of carbon, and that's the reason why if you study chemistry at the university, you do exams only on the chemistry of carbon. So there is organic chemistry, and it's a thick book with a lot of stuff in it. But if you look for it, there is no book for silicon chemistry, because silicon chemistry is much simpler than carbon chemistry. So the number of reactions that you can have with carbon atoms alone, it's a huge number. Is 100,000 reactions that you can have, and 100,000 compounds that you can form, and it's very complicated. And the reason is that carbon can form long chains of atoms, and that can be easily broken to do other reactions, but not too much easy that you can destroy that immediately. So it's interesting. It has very, very interesting properties, and you can form all these interesting molecules that are present in living organisms. Okay, with silicon you cannot do that. Okay, so there is only this superficial similarity, but the reality is that you cannot do anything like that. Of course, then if you want to, if I can make a joke, we can imagine that you can create silicon-based life forms, but in the sense that they are artificial life forms, that they are computers or that they are robots that we are building, or that some other organic being can build, and eventually they can colonize the galaxy. But of course, we are just joking. We are not sure about that. So in terms of simple chemistry, only carbon, as far as we know, can do the job. No other known compound can do the job.
That there is another question, but I think you might answer in the remaining part of your talk, which asks what are our efforts in place to investigate life outside the solar system. I think you are going to talk in what comes. So
yes, absolutely, yes. This is. I stopped here just to have the first portion of our talk, but we will see that there are other things to see. So now this is just an introduction. What we mean by habitable, which is a very restricted term in astrobiology, and then where we look for, and now we will start looking.
Another question which has been asked in this section is if both Venus and Mars are suitable and exist in the habitable zone, why do we concentrate on Mars research?
Yeah, I will address now in the remaining of the talk, because now I want to go and talk about Venus and Mars. So perhaps if there are no other questions on the first part, I can go.
There is another one which I would underline, but aren't we assuming that the way life was born here is the only way possible?
Well, as I said, we don't know how life formed, how life appeared. So certainly we don't have an answer to that. What we are assuming is that there are some specific features of life as we know it, which we hope can be common, okay, and they are not restricted only to our life. So that's why we want to give a broad definition of life. We want to be restricted only on our particular example, and we want to find only really the minimal ingredient, the minimal requirements for life. And these minimal ingredients are the ones we believe are the ones that I mentioned. So chemistry based on some complicated molecules, because if there are no complicated interaction, we cannot do anything interesting. So life has to replicate information, has to pass genetic material of some form, even if it's not exactly the DNA that we know on Earth, in some other form. But it's difficult to imagine that life doesn't replicate or doesn't reproduce, and then it has to build some machinery to do all the complicated things that cells do, and has to use the energy from the environment and all these kind of things. So that's what we believe is a general feature of life. And of course, you can have very, very different life, but we believe that the basic ingredients have to be of this kind, okay? And of course, we are looking for what we know. We cannot look for anything else, because science works by starting from what we know and then trying to find what we don't know. So we are open for surprises, but we want to start from the safe ground that we can know better.
Okay, so let's move on. Let's move on, and maybe at the end you might answer other questions. Let's go on in your questions. Yes,
absolutely. So let's start from here. Let's start exactly from this reason why Venus and Mars are so different from Earth. That's the first question. And the second question is why we are always thinking about Mars when we think about life. Well, let's look at these planets a bit more in detail, and let's look at Venus. This is Venus, okay? This is the surface of Venus, and these are the numbers that we can use to define the surface of Venus. Average temperature is 500 degrees. 500 degrees is temperature which is able to break some metals and break electronic devices, and certainly able to kill most of life we know on Earth. It's twice the temperature that you have in your oven when you bake pizza. It's really unbearable. Okay, 500 degrees is really unbearable. And also, let me point out a second number, which is the pressure. Atmospheric pressure on the surface of Venus is 90 atmospheres, which is the pressure that you have down in the oceans on the Earth. Okay, so it's really a bad place. It's not a pleasant place. And you see here one of the few images that we were able to capture of Venus was captured by a Soviet probe in the 70s, and the Soviet probe managed to survive on the surface of Venus only for a few minutes before being destroyed. Okay, so it's a really unpleasant place. And that's why we don't think about Venus too much when we think about life. But the point is that Venus was in the past probably better than it is now. And the reason why Venus is that bad today is because the atmosphere of Venus is very different from the atmosphere of Earth. And the atmosphere of Venus is basically made of greenhouse gases. So you know that the greenhouse effect is what makes the temperature of a planet higher than the temperature it would have, because the atmosphere traps the solar radiation, it traps the infrared radiation, and it heats the planet. Okay, so the planet is much hotter than it would be if it didn't have the atmosphere. So if the atmosphere of Venus was more like the atmosphere of Earth, Venus would be a good place to stay there, and perhaps there would be liquid water. Okay, but the fact is that there is all this CO2, this greenhouse gas there, that increases the temperature. So this thick atmosphere makes Venus inhabitable. So you see that it's not enough to say that the planet is close to the star or far from the star. You also have to know what is the atmosphere, because if you don't know the atmosphere, you cannot really say what is the climate of the planet. And that's why Venus is bad. And we unfortunately, we don't think that there can be any life there. What about Mars? Mars is very different from both from Venus and the Earth, although there are some superficial similarity with Earth. But Mars has a different problem. Mars is too cold. It's very, very cold. And the other problem is that the atmosphere of Mars is very thin. It's not as thick as Venus, and it's not as thick as the Earth, and it's very thin. And this very thin atmosphere means that the temperature there is much colder than it would be if there would be an atmosphere similar to Earth. So it's a complete opposite story. Mars lost all his atmosphere because it's smaller and it has no magnetic field, and there are many reasons for that. So, but the point is that Mars had a very catastrophic evolution, and it wasn't able to keep his atmosphere. Okay, and this is why Mars' surface is very hostile. The radiation level is very high. So in 5 days, you get all the radiation that you get on 1 year on Earth. And there is no liquid water. There cannot be liquid water on Mars today. Nonetheless, we think of Mars when we think about aliens and when we think about other life in the universe. And the reason for that is that in the past, astronomers believed that Mars was different than what we know today. Okay, they believed, for example, that there were variation in the season, and for some time they believed that there were artificial canals. And I want just for fun, to give you some examples of these. These are titles that were found in the newspapers at the beginning of the 20th century, where some scientists, in particular Percival Lowell, which was an American astronomer, believed and claimed that there was life on Mars, okay, and that Mars habitants were building canals on the surface of Mars, and that they were building irrigation schemes on Mars, and so on and so forth. And so he really thought that there were living intelligent beings on Mars, and this is where it started. All the idea that Mars was inhabited, and all the science fiction stories started to have to appear. Okay, during that time. Okay, but we know that it's not like that, and this is something that we should always keep in mind, that when you don't have the right instruments to look for the right thing, then you can get mistaken. And I want to show you something, which is, I mean, this thing of the Mars canals now seems funny, but if you look at the papers, this is the Astrophysical Journal and Science, which are two important journals. And if you look at this journal in the 50s, so not that long ago, okay, in the 50s, there were still papers on these journals, scientific papers, claiming that there was evidence that there was vegetation on Mars. So people believed that they saw signs in the light received from Mars. There were signs that there were plants on Mars. Okay, and now we know that is not true. So the question is complicated. It's complicated because it's very hard to get evidence about this thing if you can only look at from a distant point. But now we know that Mars is not inhabited because we've sent probes on Mars, and this is the Viking probe that were sent in the 70s. That actually, you see that there is this scoop that they got some terrain of Mars to examine it, and these probes found no evidence that there were microbes in the surface of Mars. Okay, but then we didn't stop looking. Okay, because we still think that there may be some possibility that there are microscopic organisms, some microbes on the surface of Mars. The surface now we know has some water, although it's not liquid water. There is some ice, there is some water vapor. So we have indication that water is on Mars, and also we have indication that water was liquid in the past on Mars, because we have indications that there were erosion features on Mars, and so there was some liquid water passing by. And also, and now I will show you just a quick movie that shows what we believe can have been the past of Mars and the evolution of Mars. So perhaps 4 billion years ago, Mars looked like this. So there was water on the surface of Mars, because the temperature was different, because at the time Mars still had an atmosphere, and so the temperature was hotter than it is today. And then the evolution of Mars was very bad, was not as good as the one of Earth, and Mars lost the atmosphere and lost the water, and it became, in the past billion years, it became a desert, and it became a very hostile place, which is what we see today. Okay, so today this is Mars. There is no water. It's similar to the desert here on Earth, and it's very difficult to imagine that there can be some life there, except for some very tough, very resistant life that perhaps did not survive on the surface of Mars, but found some place underground. Some microbes could have gone underground and stay there. And so we have some evidence now that there may be liquid water under the surface of Mars. This is a paper that was published on Science 2 years ago from a team, in fact, an Italian team, that found by radar, by using some radar data, found that there is evidence that there is a subsurface lake of liquid water in the South Pole of Mars. Okay, so this means that there may be some possibility that life found a way to survive, and we can go there with some drill and make some hole in the ground. And if you go down enough, you can find some conditions where life can survive. Okay, because we know that on Earth, life can survive in this condition. So this picture here shows the ExoMars rover, which will be sent in the next few years. Now, unfortunately, we don't know exactly when, because it was supposed to leave next year in 2021, but now there are delays because of the lockdown and the coronavirus. So we don't know when it's going to happen, but it will happen sometime, and we will look for life on Mars. So there is some possibility still of finding some microscopic life forms of Mars. And then the other possibility that opened in the last few years is that if you look at Earth, now we know that life can survive in very strange places. Look at these places. This is a place where life thrives on the surface of the ocean, below the surface of the ocean. Okay, and if you go down at the bottom of the ocean on the floor, you see that there are these volcans, active volcans at the bottom of the ocean, and around these active black smokers or hydrothermal vents, there are colonies of bacteria, and then there are colonies of organisms that feed off these bacteria, and they have no light from the sun. Okay, they are down there in very hostile conditions, but still life can survive there, even if it's isolated, almost isolated from the surface, and almost isolated from the sun, and almost isolated from all the other life that exists on Earth. So this tells us that life can be found even in extreme conditions. And if you look at some places in the solar system, you can find similar conditions. Because if you look at this moon, this is not a planet, this is a moon of Jupiter. It's called Europa. This is an icy moon, so it's covered with ice, but we know that under the surface there is some liquid water. And in fact, there is a lot of liquid water, because if you put together all the water that you have on Europa, is more than all the water that you have on Earth. So this comparison down in the slide shows you the comparison between the water on Europa and the water on Earth. So this is a place where you can have liquid water now, not in the past, but now. And you can also have some volcans on the bottom of the ocean. And we have partial evidence of that. We are not sure yet, but there are some evidences that things are like that. And so this is a place where you can have all the three ingredients that we mentioned. You can have energy, which is not the sun in this case, but it's the energy, the internal energy of the moon that gives these volcans the energy to be active. And then you have liquid water, okay? And we have other places in the solar system. This is another icy moon. This is called Enceladus. It's a moon of Saturn also, where there is some geyser, because there is some water under the surface that comes up through the cracks. And in the next few years, we will send probes there to analyze this water and to analyze this what happens on these moons. And perhaps we can find some evidence that there are some microorganisms. And I believe that these, in the solar system now, they are the most promising places where life could be found, because they have all the ingredients. Of course, we are not sure, because the ingredients are not sufficient, they are just necessary, but we can see, we will see what happens. So this is a very rapid idea on what happens on the solar system, and now I want to go outside the solar system. But before we go outside the solar system, perhaps I can have a very quick question if there is time, and then we can move to the third and final part.
Yes, so I picked up some questions. Like one of them is from Lorenzo De Jaco, who asked, is any mathematical model involved in astrobiology like in physics?
Yeah, that's a good question. In fact, I'm a theoretical physicist. I'm a theoretical astrophysicist. So I'm not the one that does the observations. I try to use the mathematics. And And one of the things that I'm doing, for example, which I think is interesting in the present situation, is on one side of building models of what we believe can be habitable. What is the situation where you can have habitable conditions? Okay, and this is, as I said, is a much more complicated thing than just saying what is distance from a star. So you have to build models, physical and mathematical models of what happens on the surface of a planet. And for example, I'm doing this kind of things with collaborators to see what are these conditions. But the other thing is to use statistics, because we have a huge number of planets in the galaxy. And if you don't apply the right statistic, you can have bad results. And one of the problems is that, as I said at the beginning, you think, oh, there are all those stars there. We cannot be alone. But in fact, this is a statistical nonsense. Okay, it's not true. We don't know. We have to build good models, good statistical models, to give a good answer to that, because it is not that simply because you have a lot of possibility, then you have certainty. Okay, and you know that by playing the lottery. If you know that you buy a ticket for the lottery, you are not sure that you're going to win, because there are a number of situations where you can win, but they are much less than the total number of tickets. Okay, so you have to build good statistical models. So yes, there is some mathematics involved. Yes.
Then a second question, Alberto Casalucci: what if life had already started on other planets, but it went extinct before we could see it?
Yeah, that's another very good point. In fact, this is what may have happened on Mars, for example, because Mars had in the past the right conditions for life. That's what we believe by studying the history of Mars and the fossil record. But it could have happened that life was there and it's not there anymore. And so, unfortunately, we are too late to discover it. And this, of course, can happen also for planets outside the solar system, where you only have these planets and you have a very small window of observation, a window of time where you can observe them. And you can observe them perhaps for a few years, but life went extinct perhaps 1 billion years ago, and we will never know. So it's a good point, and that's exactly what I was saying, what I was telling before. We have to build models, and one of the models, for example, that I built in the past years was a model where you have these spatiotemporal factors involved, and you can build a model of the galaxy where you see, in fact, how many planets can have time to give you the information during the time that we were observing. And so, what conclusion can you derive from this? Okay, so yes, the answer is yes, and that's exactly the kind of physics and mathematics that we have to keep into account to have good answers, because otherwise we can have nonsense.
Then Andrea Mara is asking, will Mars be habitable when the sun becomes a red giant?
Well, that's a very good question that has no simple answer, because certainly there will be a time where the sun will get hotter and things will be very bad for Earth. We know that. Earth will become inhabitable in the future, in the next 1 billion years or so. And Mars could get better in that period. But unfortunately, giving an answer to that is complicated by the fact that many things will change, not just the energy of the sun, but also, for example, the orbits of the planets. They are not stable during such a long time, so we don't know exactly what will happen to the orbit of Mars. We don't know what will happen to the orbit of Earth, and so it's difficult to do these predictions. And also another thing is that the time where the solar energy will be good enough to warm up Mars will not be probably long enough to have life appearing there. So there is no answer to that.
Yeah, then there is a question from Lori, I think. Nowadays, there is the problem of global warming. Is there the possibility for Earth to reach the conditions of Venus? Is the risk so big?
No, the risk is not so big in terms of simple anthropogenic global warming. So we know from models that even if we take all the CO2 that is on Earth and we put it in the atmosphere with fossil fuels, we would not be able to get things as bad as on Venus. But Venus had this thing which is called runaway greenhouse, which is a process which is catastrophic because you start with some greenhouse effect and then the temperature rises and then you have water evaporation and the water goes in the atmosphere and the temperature rises even more and you have more evaporation and so on, and it never stops, okay? And it got very, very bad. So it cannot get as bad as that on the Earth, but still can get very, very bad, and can get very, very bad for us in particular and for the general habitability of the planet. So would probably not get as bad as to make Earth totally inhabitable, but certainly it would get bad for us. So that's why we have to keep in mind the global warming and to have and we have to be careful and we have to change things as soon as possible, because otherwise the situation can get out of control. It probably is already a bit out of control, but we still have time, perhaps. Okay, so we have to distinguish the planetary general thing and the situation for us. For us, we need, much more specific conditions, okay, and we have to be careful.
Yeah, there are many very interesting questions, like it's difficult to pick up. So there is one which is asking, actually he asked I think twice, Guilherme Fernandez, why do we normally think that beings from other planets are more evolved?
I think that this is a prejudice, and the prejudice is due to the fact that we know that the stars in the galaxy, most of the stars in the galaxy are much older than ours, and so we believe that they appeared much earlier than ourselves, and that we arrived at the end. Okay, and then we believe that there is already this galactic lab of extraterrestrial intelligence that are much more advanced than us. But as I said, this is not necessarily true, because we don't know exactly what is the history of life in the universe and what are the probabilities. Okay, so to get back to the thing that interests me as a researcher is try to understand if the probability of having life was always constant during the history of the galaxy, or, for example, increased. And if it increased, it can mean that it was not very likely in the past to have life in the galaxy, and perhaps is getting likely now. And then we are arriving now because all the others also are arriving now, and everybody is appearing now at more or less at the same time, and everybody is starting looking more or less at the same time around, and they don't find anyone older because everybody was is all life more or less started at the same time. Okay, you have to know these things, and unfortunately we don't know. So
yes,
we can try to do some models at least to compare the results and to have some sensible answer. Okay.
Yes, so one last question now, then maybe when you finish your talk, we come back to questions. It's from Cold Scorpion. Since we look at planets light years away, is it possible that life may already exist on those planets, but we are not able to see it because we are looking at their long past?
Yes, as I said, yes, it's something we want to take into account, but also keep in mind that in reality, we are looking at planets which are very close to us, and I will show this in the remaining of the lecture. The planets that we can actually study and find evidence that there is life there are all in a small radius around the solar system. They are within, say, 100 light year. Okay, if you want to really push things very far away, they are within 1,000 light year, but it's very difficult to look for evidence of life at 1,000 light year. But 1,000 years is a very small time compared to the evolution of life. So we don't expect 1,000 years to make all that difference in the history of a planet. So we should be very, very unlucky to be looking only at 1,000 years where there is no life, okay? And we hope that this delay is not very relevant, okay? But the question is something, yes, certainly we have to keep in mind.
My suggestion is let's go on with the talk and then we come back to questions because you still have things to tell us. Okay.
Yeah, I will try to go to the last portion of the talk and move outside the solar system. And this is a picture, actually, this is an animation that shows you all the planets that were found in the last 20 years around other stars. We now know that there are planets around other stars. It's something that we didn't know 20 years ago, so it's a relatively new thing. And you see that there are many, many, many planets that we know now. And we know means that we actually know where they are. We know where the stars are, and we know that there are planets. We are not just making a hypothesis here. We know all these, these dots that you see there are systems that can be, in principle, studied with our telescopes. And you see that they have very different conditions, very different temperatures, very different sizes, and so on. So we have a huge variety now of planets to look for. We know roughly 4,000 other planets around other stars. And let me say quickly a few words about how we found that, because this is relevant for life also. We find planet in two ways. One is to look at the motion of the star. You see that when the planet orbits a star, the stars and the planet move around the center of mass of the system, and so you see a variation in the position of the star, and you can investigate this variation by looking at the Doppler shift of the light from the star. And this tells you that there is a planet. Of course, you don't see the planet directly. You just see the star, okay? But you can infer the presence of the planet. The other way we use is called, and this is called the Doppler method, okay? The other way we use is called the transit method, because it's a different method where you see the planet passing in front of the star. And when a planet passes in front of the star, the light of the star gets dimmed for a while because the planet is covering the star for a while. But of course, you can only see this in a very small number of systems because you have to be so lucky as to see the planet and the star on the same in the same direction. Okay, it doesn't happen every time. You have to be lucky. Okay, and the other thing, let me show you what. Because this picture shows you something very idealistic, but let me show you a real transit, a real transit of a planet of our solar system, and this is Venus transiting in front of the sun. So you see, that little dot is Venus transiting in front of the star of the sun. So if you want to see the same thing on another system, you don't see the star as big as we see the sun. You just see a dot where the star is, a dot of light, and that that planet passing in front of the star should really be doing a very, very small effect. But we can measure it with the data we have now. Okay. And this is how we find the planets around other stars. But now, the thing we want to do, okay, this is just a summary of all the planets that we discovered. I won't go into the detail here because we don't have enough time. I already said you what I wanted. But let me show you this interesting thing, which is a periodic table of exoplanets. Periodic table is, by analogy with the periodic table of elements, this is a periodic table of planets where you have the parameters of the planet. So you have cold planets and warm planets and planets which are big as Earth or smaller than Earth and so on. And so you see that there is a distribution of numbers here where you see that there are many planets which have a size similar to the Earth and the temperature similar to the Earth. And so these are the planets that are more interesting, the planets that we will look at in the future, because they are planets that are good candidates to be inhabited. We don't know. We have to look better, okay? But this is where we will look. And so this is a summary of the potentially habitable exoplanets that we have discovered. And you see that it's interesting because actually there is one planet which is in the habitable zone of the closest star to the Sun, Proxima B. It's only 4.2 light years away. And all these planets, you see, all these potentially habitable planets are within a few tens of light years from the Earth. Okay, some of them are farther away, but you know the closest one are planets that we can study in the future. And for example, this is Proxima. Okay, this is the planet around Proxima, showing the similarity with the Sun. It's very different. It's a very different star. It's not like the Sun. It's a small red star which emits much less light than the Sun. So the system is much more compact than the solar system. And we don't know if there can be life around a star which is very different from the Sun. And this is one of the things we have to understand in the future. And this is another very famous system, which is called TRAPPIST, where there are 7 rocky planets, and some of them, probably 3 of them, are in the habitable zone. But let me remind you once again that if you look at the solar system from outside, you believe that also Venus and Mars are in the habitable zone. So it's not enough. But still, this is an interesting place to look in the future. And because it's not very far away, just 40 light years away, we can look at them with telescopes, okay? We cannot get an image of the planets yet, but perhaps in the future we will be able. And what we will do, well, let me show you this paper. This is a paper by Carl Sagan and others, a paper that was published in Nature in the 90s, where they had this idea: let's use the Galileo spacecraft, which was a probe that was leaving Earth, going outside Earth towards the Jupiter and the outer solar system. But well, let's use the instruments on board this Galileo spacecraft to look at Earth. And let's try to see if there is any indication from these measurements that there is life on Earth. Of course, we know the answer. So this is the most unsurprising paper ever published on a journal, on a scientific journal. We know the answer. We know that there is life on Earth. But the point of the paper is to show you that you can find evidence of life on a planet, even if you look from outside. There are some indications. Of course, let's remember the case of Mars, where we mistakenly believed that there was life when in fact there wasn't. But also keeping in mind that example, let's also be optimistic and know that there are some indications that we can find looking to a planet from very far, from the light of the planet. So there are things that we can do. For example, you see here when a planet transits in front of the star, as I showed you before, you don't just see the planet. You also see the light of the star going through the atmosphere of the planet. So when you look at the atmosphere here, at the light of the way the light of the star is modified by passing through the atmosphere of the planet, you can infer some information about the composition of the atmosphere. And so you can find evidence that there are, well, first of all, you can understand what the atmosphere is, which, as I said at the beginning, is very important to know the real temperature and the real climate of the planet. But also you can find traces of elements in the atmosphere that can tell you if there is life on the planet. And also you can find some indication about the surface property of the planet, because when a planet goes back and is illuminated, is lit by the light of the sun or the star, you can find some evidence of how it's done on the surface. Okay, so in the future we will get more and more clever and much better in doing this kind of observations. And what we find is that, well, if you look at the atmosphere of a planet where there is life and a planet where there is no life, they are very different. So there are spectral signatures of life that you can discover, for example, oxygen or methane or other gases that are related to the life. Okay, and so this is what we want to do in the future with exoplanets. We want to build the spectra of the atmosphere and see if there is any life. Okay, so this is the general idea. Okay, I hope I gave you enough information and enough stimuli to get some curiosity about what we're doing. Of course, I had to be very synthetic now because there is much more that one can learn. But if you are interested in these kind of things, keep in mind that there is people investigating this, and it's a very active field of research. There is astrobiologists, and I teach astrobiology in Tor Vergata if someone is interested. But in general, it's a field where we expect to have very, very strong advancements in the next 20 years. So it's something for young people. Thank you. I cannot hear.
Sorry, it's my fault.
Yeah, okay.
I have some time for questions.
Yes.
So I'll start with some of them, like one which was put by Parsa Eftekhar. Why Mars lost its atmosphere?
As I said, the overall process involves many factors. One factor is Mars is smaller than the Earth, so the surface gravity is much lower than on Earth, so it's much more difficult to keep the atmosphere there for a long time. So this is one thing. The atmosphere, in general, the atmosphere is a complex system where you have to have equilibrium between different factors. Some factors are putting atmosphere, and some other factors are getting rid of the atmosphere. So you have to have a balance. If this is not in balance, you lose the atmosphere. So the atmosphere, the Earth is losing some atmosphere, but fortunately we have other effects. For example, volcanism, where you have the atmosphere, the gas trapped in the crust and in the mantle, which is put outside by the volcans. Okay, but Mars was smaller, less gravity, so atmosphere got lost, and it wasn't replenished because at some point the volcanism on Mars ended. Why the volcanism ended? Because Mars is too small, so the internal heat was dissipated more easily and more quickly than on Earth, and so at some point the internal heat was not enough to drive volcanism. Okay, and so you have no volcans, you have a small gravity, and another thing is that you have no magnetic field. And the magnetic field is a protective screen from the charged particles coming from the space, like cosmic rays, okay, or the solar wind. The solar wind is made of charged particles, and they are very energetic. And when they hit the atmosphere can get lost because of that. But if you have a screen as Earth, where you have a magnetic field, this effect is much reduced. If you have no magnetic field, as on Mars, then the effect is much worse, and you can lose much easily the atmosphere. Okay, so it's a combination of factors, and all of that eventually boils down to the fact that Mars is smaller than Earth. Because also the magnetism is related to the internal heat and to the fact that you have a core of liquid metal, okay, and if the core is frozen, you have no magnetism.
Then I combine two questions which are not necessarily directly related with your item, but they are still interesting. So the questions are from Francesco Stefanelli and the other one from Paris K, who asked, is it possible that we could move to Mars in few years? And the second one was, what do you think about the SpaceX plan about moving to Mars?
Well, they are related, because I don't think that we are going to move to Mars in the next few years. I think it's unrealistic. And I think that certainly we will try in the future to send humans on Mars. But in terms of what we can learn scientifically, we can learn a lot without sending humans. And it's very, very dangerous to send humans on Mars, because it's not as easy as going on the moon. Going on the moon is difficult, but it's easy compared to going to Mars because of many things that can go wrong. The travel time is much longer. And also, the thing that everybody forgets is that there are radiations. And if you want to go there and you spend overall 3 or 4 years by going there and then staying on the surface and so on, you get a lot of radiation, and you have to screen from those radiations. So this means that you cannot go there unprotected. You have to build a spaceship which is protected by radiation, and also you have to build habitats on Mars to screen your crew from radiation. So it's complicated, and I don't think it will be done immediately, and I don't think it will be done in the next 30 years. And I think that Elon Musk did a lot of interesting things, and with SpaceX is cool and it does very interesting things. But I think that when he tells that we will go on Mars and put colonies on Mars, he's far too optimistic, and I believe a bit unrealistic. So the other question is if we can colonize Mars, and the answer is contained in the other answer. I don't think we can colonize Mars quickly, and certainly it's difficult to change the conditions of Mars globally. We can build habitats, okay, but this will take a long time. It will take a century, I believe, or more. And it's not clear if anyone will have the reasons to go there. You see that Earth faces a lot of problems now. One is global warming. Now we have this problem with pandemics, which will be probably a problem that we have to face in the future. And I don't think we will have the resources and the reasons to go on Mars quick. Sorry about that, but this is my realistic take on that.
Then we go to the question asked by Giorgio Baglioni, who asked, why exactly the size of a planet matters when searching for life?
Because, as I just said, in the case of Mars, there are relations between the size of the planet and what can happen on the planet in terms of climate, atmosphere, habitability. All those things are related. And so it's not just because we want planets to be exactly identical to Earth, because that would be stupid. We don't believe that we are so important as to be, the only place where life can possibly appear. But still, we know that there are some ranges of radius and dimensions of planet which impact on the habitability. And we see the case of Venus and Mars. We see, we have models that tells us that if you get too big a planet, for example, it's very hard to get rid of the atmosphere. So if you get a big planet, because planets form in an environment where there are other gases and hydrogen and helium, if you build a big planet, then the planet gets all these hydrogen and helium in the atmosphere, and you get a very thick atmosphere. So instead of having a small planet, you end up with a planet which is similar to Jupiter, okay, where you have all this envelope of gas. And that's not a place where we believe you can find conditions for habitability. Of course, we don't know. I mean, as I said, we always leave an open window on that. But if you want to have some environment which is what we believe is habitable, it cannot get too big. Of course, there are planets which are called super Earths, which are a bit larger than Earth. so they're like 2 times larger than Earth in radius, which can still be habitable. And actually there are some studies, some theoretical studies that tells us that perhaps they're even more habitable than Earth. So this is not to say that Earth is perfect, okay? You can do better, but the size matters.
Then I'm reading to you a very interesting question to me. So from Lorenzo De Iaco, it's asking you, how do you convince people to put money into astrobiology research?
I don't convince them, in fact. It's very difficult to convince. Now, joking. It's not that difficult these days because the situation changed a lot in the past 20 years. Because astrobiology some years ago was a very speculative endeavor. There were no data, basically. There were no space missions. There were no exoplanets to look at. And so people was not very keen on investing on that. But now things are different because as I said, my main point is that we know much more about life on Earth, and we know that life on Earth is tougher than we believed. So life can survive in very difficult conditions. We know much more about the solar system, and we know places where we didn't believe initially that could be conditions for life, and now we believe there may be. And we know much more on the exoplanets, and this was the real revolution, because now we have thousands of places to look for, and some of them, tens of them, can have the right conditions. And now we know that in the galaxy there can be billions of habitable planets. And so this is what now makes astrobiology so exciting. And it is so exciting that personally, for example, I come from a very different background because I was a cosmologist, and I still am a cosmologist, but I moved totally now to astrobiology in these days because I believe it's more promising for the future than other fields that are less interesting from my point of view, of course. So we go there and we ask for money, telling this story more or less.
Yes. Okay. So then let me look. There is another question. Well, actually, two which are similar. So one, it's from Rodrigo Ferreira, who asked, how do we know the internal structure of other planets? And in the same time was a question from Emmanuel Nocera, who asked, how do we know how much water there is on other moons?
The water there is on other moons, as Europa or Enceladus, is based on studying what we can see of the moon and making models, of course, and then comparing the models to what we see. So it's not a direct evidence, it's not a direct investigation of how much water is there, but planets can be modeled because we know its composition, we know it's the diameter, we know how much internal heat is there, we know many things, and we can build a model, and then the model tells us some plausible answer about how much water is there. And so that's the question. And also this is a question that partially answers the other question, which is the internal structure. Of course, we don't know the internal structure, and the only thing we can do is build models. So again, it's a mixture of theoretical modeling and trying to compare this modeling with what we can really observe, which is the way that normally science proceeds. You build model, you compare to observations. The difficulty here is that in physics, sometimes you have very simple system, and you can do simplifying assumptions. With planet is difficult because you have many more variables involved. But we have also a very advanced theoretical knowledge of many of these things, so you can build realistic models. Of course, we cannot tell if you look at an exoplanet, we cannot tell for certain what is the internal composition. But if we assume that is similar to the solar system in composition, and the formation history was similar, then you can make some predictions.
Okay, so now I ask you the last question, and before your answer, I want to thank to all those who were following us and tell you that we will be back tomorrow at 10:30 with a new series of 2 lectures where you can interact with us. So the last question I pick up from you for you, it's don't we need to be careful to not contaminate other planets with terrestrial microorganisms when we send some rover to another planet?
Absolutely, absolutely. And in fact, this is a real source of preoccupation, and there are people dealing with this, and there is a protocol which is called Planetary Protection Protocol by the NASA, and it's subscribed by other space agencies. Let me also add that this is a recent preoccupation, a recent concern. It's something that we started to be worried only in the past few, 10 or 20 years or something. And not enough precautions were taken with the old missions. For example, the Viking that went there in the 70s, they were sterilized, of course, but they were not sterilized as thoroughly as we think now that they should have been sterilized. So we probably already sent some microbes on Mars. We don't know if they survived. There is a possibility that they survived. But this is something we should be careful about. And this is one reason why I believe that talking about, for example, terraforming of Mars, altering the surface of Mars with, some engineering or stuff like that, it's a crazy idea because we actually don't know what's going on there. That could be, in principle, microscopic organisms that could be killed by this process. So I don't think it's ethical to do that. We should be very careful about that. And another thing I want to add is that this also tells us that in the past, in fact, there certainly was transfer of material between the Earth and Mars and vice versa, not because of space missions, but because fragments of the Earth were brought to Mars and vice versa in the form of meteorites. Okay, so there is this theoretical possibility that Mars and Earth are close enough to have been cross-contaminated. And so there is this theoretical possibility, just speculating, that life appeared on Mars and then was transferred on Earth by some rocks, or that life appeared on Earth and then went to Mars by some rocks. So if one day we find life on Mars, which we hope so, we have to be sure that it's really different from terrestrial life. If, for example, we find that they have the same DNA and they have the same structure in the cells, and that they have the same amino acids and the same chirality and so on, then we can get suspicious that they didn't have an independent origin, that they originated in the same place and that the planets were just, contaminated with each other. So let's hope that we find something very, very different, so we can be sure that they originated independently.
So thank you very much, Amedeo, for this lecture. Thank you all for following us. I've seen a question which asks us where you can find the presentations. We shall try to put the presentations on the dedicated webpage, INSPYRE 2020. So look there. So thank you all for having followed us today, first day of INSPYRE School. And it will last all the day. We will have 2 lectures per day starting 10:30. So I can only wish you a very nice day for what's remained of the day, and meet you again online in the lectures which are going to be held tomorrow. Bye-bye, guys.
Bye-bye.